Hello and welcome to INE's CCI Service Provider version 5 Learning Path. Today in this course we would talk about implementing control plane security. Now the first thing that you need to know to understand control plane is what exactly is control plane. Control plane is basically just a logical grouping of all different protocols or even information like signaling or link information could be control plane. There are different types of control plane protocols. We have OSPF, ISIs, could be BGP, could be ICMP, could be LDP, RSVP, or even protocol independent multicast, which is PIM. Besides that, we also have something like ARP. ARP information could also be control plane information, or even BFD could be control plane information. So learning about networks from different routing protocols, that's control plane. So let's say if you and me are OSPF neighbors, and if I send you an update, which is an OSPF update, giving you information about my networks, that's control plane information. Protecting the control plane is really, really important because without control plane protection, anything that happens in the data plane could affect the control plane. For example, let's say if there was a DOS attack as far as your data plane is concerned, if there was a DOS attack, it could affect your control plane, which could bring your entire network down. So there are different ways of actually protecting your control plane. The first method could be maybe by disabling IP ICMP redirects. Now think about what ICMP redirect does. So let's say if you, me, and a third router, we were all in the same subnet. If router A does a ping to router B and the destination is supposed to be router C, so maybe what's going to happen? Assumingly router A needs to get to router C and his next hop is router B. So think about like a DMVPN environment, hub and spoke. So spoke A wants to talk to spoke B, but he has to transit the hub. So if you and me are in the same subnet and traffic is coming into the hub and going back out the same interface to the remote branch office, what's going to happen? The hub is going to basically send an ICMP redirect message to the spoke saying, hey, you do not need to come to me. That's an unoptimized path. You can go directly to this neighbor. Here's the next hop. So that's exactly what happens in ICMP redirect. So a hacker could basically use this information to exploit the router by he would constantly send ICMP or ping or any echo request to the hub router so that the hub router generates ICMP redirect messages. If I constantly do that, what's going to happen? My CPU would keep going up. And because of that, it could cause disruption in the network. So protecting that becomes important. You should disable ICMP redirects on the router. An ICMP redirect happens automatically when there are more than two routers in the same broadcast domain, and if the packet coming into the router has to go back out the same interface. In that case, the hub router would send an ICMP redirect message back saying you are using an unoptimized path. So a hacker basically exploits that and causes your CPU to increase. Now iOS XZ routers and XR routers basically have IPv4 redirect disabled by default. If you do want to enable that, you can enable that. For example, if I go to my XR router and let's look at my interface, show run interface gig 0000.619. As of right now, the only thing that I have is an IPv4 address and an IPv6 address. If I do want to enable ICMP redirects, you can, but normally you should not enable that. That is disabled by default. So if I go back to interface gig 0000.619, here you'd be able to see that if I need to enable that, the command is IPv4 redirects and commit. So now ICMP redirect is enabled on that interface of the XR router. By default, it is disabled, which means if I do receive a request from spoke 1 destined to spoke 2, when the packet comes into the hub router, it has to go back out the same interface through the tunnel to spoke 2. So the hub would not send an ICMP redirect message to the spoke 1. So it has to basically rely on other protocols like maybe NHRP, maybe DMVPN phase 2 for spoke 1 to go to spoke 2. The second way of protecting the control plane would be by dropping IP directed broadcast. Basically, all directed broadcast should always be dropped. Now, what exactly is directed broadcast? Is that enabled by default? Most routers have it disabled by default, but you should never enable that. But if you look at from a directed broadcast, what happens behind the scenes? So let's say if I am an attacker, I send a packet, an ICMP packet, to a destination subnet by spoofing somebody's IP address from that subnet. What's going to happen? So I have spoofed, let's say 10.0.0.1, somebody's IP address. I don't belong to that subnet, but I have spoofed somebody's IP address, and I send an ICMP packet as a broadcast in that subnet. What's going to happen? Everybody in that subnet is going to respond back to the spoofed IP. And that can cause a problem in your data plane, and it can eat up your CPU. So dropping directed broadcasts is a good thing because that protects you from DOS attack, mainly Smurf attacks. Cisco IOS XR routers has directed broadcast disabled by default, but if you do want to disable that, let's say if it was enabled, then you can disable that with the command no IPv4 directed broadcast. Let me in fact show you that. Right now, if I do a show run, it is disabled by default. But let's say if it was enabled, you would see it on your interface. It has to be done per interface basis. So interface gig 0000.619, and if I give the command IPv4 directed broadcast. So if you go and do a show run and if you see this command enabled, you should go and disable that, because if this command is left enabled, it can cause problems because you're basically open to Smurf attacks. Let me show you a show run. Show run interface gig 0000.619. So now I have directed broadcast enabled. This should be disabled to protect your control plane. Now, control plane can also be protected by disabling IPv4 source routing. Now, in IPv4 source routing, it basically takes the advantage of loose source route or even the strict source route to specify the packet that which path it should take. Now, attackers could use this as an advantage by modifying the IP datagram and define which path it should take to avoid going through security firewalls. So you should disable IPv4 source routing. Now, depending on the version, whether it's an iOS XZ or iOS XR routers, it may be enabled. If it is enabled, then you should disable this. To disable IPv4 source routing, it's a global command, and the command is no IPv4 source routing. Let's see this command on the iOS XR. We'll try and disable this. So the command is IPv4 source route. And let's do a commit if you want to enable this. So if it is enabled, you should disable this to avoid allowing attackers to modify the IP datagram so that they can specify the path. So any packet which is received which has the record option enabled in the header, your XR routers would basically drop that frame and not process that packet. To disable it, the command would be no IPv4 source route and commit. The next way of protecting the control plane would be by disabling ICMP unreachable messages. As you know that ICMP unreachable messages are generated by the routers to instruct or tell the source that the destination is unreachable for some reason. So this type of an unreachable message is basically a type 3 message. So what's going to happen? A hacker could probably exploit this by sending you continuous ICMP echoes, and you would keep sending back unreachable messages, which basically increases your CPU. So people could exploit this feature That's why you should disable ICMP unreachable also on the router. However, there are many different types of ICMP messages. For example, there are approximately around 16 different types of ICMP messages or types which are available, 0 to 15. For example, if you look at an example of traceroute, traceroute uses ICMP type 3, code 3, to basically detect or tell you that when it reaches the last hop. So sometimes you may want ICMP unreachable message to be kept on. You don't want to disable that. So in that case, to protect your control plane, what you could do is limit the amount of unreachable messages being sent from your router back to you. So by default, it sends one unreachable message every 500 milliseconds. You can control that. You can define that, okay, send one every 1000 milliseconds. You can change that value. Let's in fact see that. To disable ICMP unreachable message, it's an interface-based command. So go back to your interface and say interface gig 0000.619. Here I would say IPv4 unreachable disable. This disables unreachable messages, or basically ICMP unreachable messages on that interface. But let's say if I wanted to keep this on to allow other type messages to work. So in that case, what I would do would be, instead of disabling this, I would go back and globally I would define the ICMP rate limit so that I don't send one unreachable message every 500 milliseconds. Instead, I would say ICMP IPv4 rate limit unreachable, and define the timers, which basically says that default is 500 milliseconds, but now I'm going to send every maybe 2000 milliseconds, I'm going to allow one unreachable message to come. So this basically reduces the CPU, because now if somebody exploits that and keeps sending you multiple pings, echo requests to a destination which is unreachable, you would keep sending unreachable messages back. But now I'm controlling that by saying I would only send one unreachable message back every 2000 milliseconds. Now, Cisco IOS XR routers has something built-in protection for the control plane, which is for any packet which is received, which has an header option enabled. It basically causes or has two concerns for security. The first one is that any packet which has header option set basically has to be process switched. The second problem or the concern is that if somebody sets the source route option, which basically tells the packet to modify its path, by default an XR router will drop anything, as discussed earlier, that it would drop anything which has a source route basically in the header defined. But any other header option which is enabled in the IP datagram, the XR routers would basically punt that and basically limit that traffic using policers. XR routers do that automatically to protect your CPU. But let's say if you did not have XR routers, you had IOS XZ routers, that does not happen automatically in IOS XZ routers. You have to use maybe a rate limit or a policer to limit the amount of traffic on that interface. Now, fragmented IPv4 packets cause or pose basically a separate challenge for the network. Normally, attackers use fragmented packets to avoid detection by access lists or by firewalls, because these fragmented packets gets punted on the line controller and causes high CPU on the devices. So you should basically disable or at least rate limit your fragmented packets. Rate limit can be done with different options. We have policers, or we can do QoS on the interface, where we define that if the packet is fragmented, then limit him to a certain amount. Or we could also disable or disallow fragmented packets by using an access list. So maybe let's say if I had to disable fragmentation for all traffic, then I could just say deny IP any fragments, which basically drops fragmented packets and allows all remaining traffic to go ahead. So you should disallow or at least rate limit your fragmented packets, because most of your DOS attacks, attackers normally use for DOS attacks fragmented packets to avoid detection by the firewall. Now, Cisco IOS XR routers has basically developed many features or many ways of actually protecting your control plane. Here are some of the list of some protocols which are basically protocol independent, so ways of protecting the control plane. The first one could be maybe you do an IGP MD5 authentication to protect your control plane, so never have your OSPF adjacency without authentication. Different protocols support clear text, different protocols support HMAC SHA, they support MD5 also. You should at least do MD5 or HMAC SHA depending. You should never do clear text, depending on the routing protocol again. So you should have at least some kind of authentication between the neighbors, because you don't want any rogue router sending you an update and modifying your routing table. So you should have an IGP-based authentication to establish adjacency. The next way to protect your control plane would be maybe keychain management. So again, I could define a predefined password between you and me, which is again less secure. Using keychain is better because you can have a keychain rotation configured where you could change your passwords at certain intervals. So you should have multiple keys defined, maybe every week change your passwords or every month change your passwords by doing keychain rotation. Another way could be IGP TTL security, which can be configured. For example, let's say OSPF. As you know, OSPF sends hello packets and also sends updates by using LSAs. There are different kinds of LSAs available in OSPF. But network attacks could occur when LSAs are being propagated, because there's no specific guarantee that the update or the LSA came as a unicast or as a multicast from a neighbor who is directly connected or maybe a few hops away. For example, a virtual link. A virtual link neighbor may not be directly connected. He may be a few hops away. So there's a possibility of an attack happening when LSAs are being flooded. To prevent that, you could probably have a TTL defined for your virtual links, which basically limits that, okay, my neighbor should be maximum 2 hops away. So I could define that for my virtual link in OSPF. The next way to protect your control plane would be maybe configure passive interface. So interfaces where I'm not supposed to have neighbors, but I still want to advertise that link. I could probably do a passive interface. Don't activate IGP on links where you don't need. Configure passive interface instead. Then you could also limit the amount of routes being redistributed in an IGP. So let's say if I was using OSPF as my IGP and there was a BGP router running somewhere and that router redistributes all the BGP routes into OSPF, what's going to happen? Your routers will crash because too many LSAs, too many external LSAs are being learned. So you can also limit the amount of redistributed routes in the IGP. Same thing can be done for ISIS also, where I could say that the maximum amount of routes that I would accept from, let's say, a neighbor or which is redistributed would be maybe 5,000. I can limit that amount. You could also use RPL, which is routing policy language, to basically create basically some kind of filter, maybe do to filter some routes from a neighbor or have neighborship with a specific router, or maybe filter some BGP attributes, which can be done with routing policy language. The next way could also be to use BGP TTL security. So as you know, in BGP, we have 2 different kinds of BGP neighborship. We have eBGP, we have iBGP. iBGP has your E multi-hop is by default set to 255, but for eBGP, it is 1 by default. Now imagine if an attacker wants to exploit or cause your CPU to go high. What he could do is he could send you constant TCP SYN packets towards your eBGP peer. Maybe the attacker is 255 hops away, but he would keep sending you TCP SYN packets to cause your CPU to go high because your BGP has to process that packet. So now to avoid that, I could enable TTL security. What that does is it changes the E multi-hop to 255, but sets the TTL to 1, which means that I am limiting my attack And the only possible attack could be from my directly connected neighbor. Nobody else could reach me or send me a TCP SYN package towards my BGP because my TTL is set to 1, because it's going to change at every hop. It's going to reduce by 1 at every hop. By me setting the TTL value to 1, I am saying that I am only going to farm or respond to my neighbor, which is going to be directly connected. Another way would be to ensure that your BGP neighborship is authenticated. As you know, BGP uses MD5 for authentication, so you should have at least MD5 authentication enabled between the neighbors. You don't want your neighborship to be without authentication. Another way to protect your control plane would be to define BGP maximum prefixes, because the more amount of prefixes you learn from a neighbor, the more amount of memory is going to be utilized. So imagine if a neighbor who wants to attack you, or some device who wants to attack you, he starts sending you thousands and thousands of routes. All of these routes are basically stored in your memory. So the more amount of routes I receive from a neighbor, the more memory is going to be consumed. To prevent that, I could define the amount of maximum prefixes I can learn from that neighbor. So restrict it per neighbor, how many prefixes I can learn from that neighbor. Lastly, you can also protect your control plane by protecting your MPLS or your LDP. So your LDP neighborship should be authenticated again so that you have a secure LDP connection with your neighbor. I hope this video was informative to you, and thank you for viewing.